If you look at design, this is a figure we have shown in one of the last webinars. These are the 4 big categories of factors that drive the ozonation process, performance, and cost. So performance means removal, but also bromate formation, transfer efficiency, things like that. It's all about process parameters. How do you operate your process? Gas, water flow rates, dosing locations. That's operational. On the other hand, as an engineer, of course, you have to design it. So it's all about the reactor, the transfer equipment you use. Of course, we already talked about it. You have the water matrix as well. And then you have the human factors, of course, the operator that is operating a plant, or how do you operate it? If we zoom in on these two, these are the two you design for. You can choose as an engineer, and you can actually impact. And we will now go to Italy again, to our colleague Giacomo, and he will be demonstrated that actually your choices matter. So which choices you make here really, really matter. So Giacomo, the floor is yours.
Thank you. Thank you. Let me share my screen and I'll bring you to my laptop, in which you can see a full-scale installation represented with a general injection system here. That can be diffusers, can be side stream injection or hybrid systems. And then you have the flow going through a couple of reactors. This is an installation of a total 100 cubic meters. And then there is an influent going in, which we can run dynamically, an influent going in with a couple of days of dry weather, and then a rain event that will hit the plant in the 3rd day. At a certain point, you will see our bypass will take action and avoid that the whole gigantic influent goes through the ozone installation, but just the maximum capacity of the installation. Now you see the flow rate going through our plant, the daily dynamics. We are passing through day 2, and now we can check the HRT of our installation, which is rather high. It's 37 minutes in total, almost 40 minutes. And now the rain event is hitting our installation. So a maximum of 2000 cubes, it's passing through the plant. So what if at this point we decide, okay, so we have some room with HRT, but what about to reduce the installation? But how about our residuals of ozone? Now, if we look at the residuals of ozone, we already see that a reactor 2, we don't have any, even though we have a big flow coming through, and reactor 3 actually is not in use. So we could actually sensibly reduce the size of the installation. Here I'm making just a change, reducing the whole installation volume by 30%, and then we can continue the simulation here, and then we can watch how that reflects in terms of micropollutants removal. Here we see that the average removal doesn't change significantly. Why? Because we still have room for complete exposure to the dose that we're inputting. Here we see an increase in the removal due to the rain event, which is lowering the strength of the water and then making the life of ozone and radicals longer. And now we can see that the rain event, in which we had a minimum HRT of 7.2 minutes, is now causing another peak event is causing the HRT of 5 minutes, which is completely reasonable if we look at the residuals, which are very reasonable, especially at the effluent of our installation, because we are far below at any detection limit in this case. So, and with this, we can go back to the presentation, and I'll show you later another demo. Thank you.
Thank you, Giacomo. In the meantime, we got another question coming in from Mohammed, who is wondering if we consider resident time distribution model to evaluate the behavior of fluid inside the reactor, or using CFD model?
Yeah, this is a perfectly timed question, Mohammed. Thanks, Charlotte, for bringing it forward. Because this brings us to the CFD slides. And yes, full-scale reactors have non-ideal dynamics. So mixing is very complex. You always have some short-circuiting, some dead zones. For example, in this reactor, you can see some rotating zone. I agree, it's a poorly designed reactor, this one, but we are showing a quite extreme case in this case. And yes, if we model full-scale plants, we try to, usually we were involved in the design stage where we use CFD to help designing the reactor. Based on exactly the same model outcomes, which we used for the design, we transfer that to the environment Roberta and Giacomo have shown, and we construct a better model with it. So we have some methodologies for that. And yes, so this allows us to include residence time distributions in it very realistically. And this is the best of both worlds because you still have a dynamic model that runs very fast, but still you have the realism of a CFD model in terms of hydraulic representation. Yeah, we are not going into this methodology in this slideshow, but if you want more information on that, you can always drop us an email. So talking about CFD, well, the message we want to give under this point is your choices matter, but you can really impact a lot yourself. So you can really impact a lot in the design stage. You can use, for example, the sizing. If you look at this reactor, you see the ozone residuals going through a reactor under and over the baffles. In this case, yeah, for example, 40–50% of your reactor has almost no ozone or no ozone actually. And if this is happening at an event where a lot of ozone was dosed, you can ask yourself the question, can we maybe not design it a bit smaller here and still account for the peaks safely? That's one thing. And then, of course, you can start detailed designing. Where do you put baffles? Can we further knock down bromates? Where should we add peroxide? Or how to improve the ozone dissolution? You can use CFD for that. In this case, you can see the impact of hydrodynamics on bromate formation in a full scale. And if you don't care, if you don't really pay a lot of attention, you might have some hotspots of bromate in your installation. You can not only, well, it's not only reactor related, you can also talk about equipment. For example, this is a more of a pipeline flash reactor with a static mixer. You can look at the dissolved ozone going through, or you can also look at Venturi pipes in detail to better design equipment. So your choices really matter as long as you understand the impact of your assumptions and also the matrix, take it into account. But we are 2021 and a lot of tools are at our disposal.